Hi, my name is Frank, and I saw on the internet a lot of attempts to solve this cube puzzle where you measure the resistance of, it's 12 resistors in a cube, and if you measure the resistance at different points, you get different values. But anyway, I saw a lot of videos on the internet on this, and I came up with a way to solve it also. I don't know if my method's any better or not, but it's a more sure-shot way of doing it. You could do cubes, whether all the resistors are the same or different, or it could be a tetrahedron, it could be all different shapes, it could be capacitors, inductors. It's a more general way of solving this problem. So I'd like to teach this to you as it can make you a much better electrical engineer. Anyway, if you want to go through my little presentation here, you can learn how to do this also without too much of a struggle. Okay, so this is the resistance cube puzzle, a more general solution method. So this is a more general way of figuring out the equivalent resistance of the cube without having to worry about symmetry and redrawing it. This works for a lot of different circuits. I use this method to analyze circuits all the time, whether they have resistors, capacitors, inductors. Seems to work pretty well. So I would first like to give you the answers to the problem, then show you how to perform the analysis to determine the answer. There are three different equivalent resistances on this cube that can be determined. Thereby, three examples are provided in this lecture. So this is example one. Now, example one is if you had this cube of all resistors, and the resistors can be different or the same using this method. It doesn't matter, but in our case, our simplified example, we're going to make them all the same just because we know the answer to that. So I call this example one. Now, example one is going to be what is the resistance from this point, I call the VA or point A, node A, to H. So the next example is example 2, and that's going to be what is the resistance if you measure between node A and node B. And example 3 is what's the resistance going to be if you measure from node A to node G. So all the other possible nodes are similar, like say going from A to B, you get the same measurement as going from A to D because of the symmetry of this object. So anyway, the situation is we put an ohm meter between this node A and node H and measure resistance. Now the ohm meter that we use, it actually outputs a voltage and has a ground. So the way it runs the test, it does put a voltage in to this device. It might be a very small, low voltage and measures the current. So the trick is that this current, when it comes out, it breaks up into three different paths. So I called them, one path was IAB, which is this path, IAD, which is this path, and IAE, which is this path. But this would be the current going down this representation of a battery. So say it's 1 volt, it could be 1 volt. It's very arbitrary, but let's just say it's 1 volt. So the total current, I called it IN, is the sum of these three currents, IAB, IAD, and IAE. So the way the voltmeter works or ohm meter works is that it takes the voltage, it knows its voltage at this point and divides it by the current coming out. So the equivalent resistance is going to be the voltage divided by the total current. So that's how basically like the ohm meter computes the resistance by doing that measurement and doing that computation. So we're kind of going to do it in the same way, maybe as a ohm meter works. So anyway, there's 12 resistors, kind of 12 edges on this cube. So there's 12 resistors. So I designate them like we have these nodes. There's 8 nodes. So there's this node A, B, C. Then we have D, E, F, G, H. So it's kind of arbitrary how you name them. It doesn't really matter how you call them. But I put these resistances in. I call it RAE, saying it's from A to E. Now it could just as well have been REA, which but I used the convention I'm using like the low, like the highest letter to like the lowest to highest letter. So I'm trying to do it in that order. It doesn't really matter, but I was trying to do it just for consistency. So I put here all R's are 1 ohm, and that's not quite true. It could be whatever you want to set them to, but to simplify the problem, I set them to 1 ohm to make it easier to do. So anyway, so we consider our power source coming from the voltmeter or ohm meter, or we call it a voltmeter because it's a multimeter. It does resistance. So I have it represented by a battery, and then it's applying a voltage to this node. So this node is known. You know what this node is because that's what the voltmeter is applying. And you also know this node. I said this was ground, so I said this was 1 volts and this is 0 volts. So anyway, so we have 12 resistors and we have 8 nodes, and there's basically like 8 equations of motion. There's going to be 8 equations of a motion that we need to look at for this. So anyway, I just wanted to give you the answer. So the answer to this, if we measure the equivalent resistance from node A to H, so I have REQ A to H, is 3 times R over 4. That's if all these R's are the same. So you could say all these R's is equal just to R. So it's 3/4 of R. So that's the answer for example 1. So I just wanted to give you the answer first, as I saw a lot of these videos, they don't give you the answer to the end. I want to make it a little bit different and give you the answer at the beginning. So the next example we call example 2. So in example 1, we did the corners. We went from this point A to H. Okay, so but now we want to go from A to B. It's an edge. So it's a similar situation again. You have these 3 currents, and there's a total current coming from the ohm meter, and there's the way the ohm meter works. It computes its equivalent resistance from VA over current in. Now the difference, before we had the ground over here, but now the ground we moved it to B. So we're going to measure the resistance from A to B. So anyway, I went through the math and also did some measurements on a real device. And let's see. So for example 2, if all R's are equal to R, determine the equivalent resistance from point A to point B. So what's the equivalent resistance from point A to B? So the answer is 7/12 R. So it's 7R times 12, 7R divided by 12. So if R was 1 ohm, the answer would be 7 over 12 ohms. Okay, so that's for the edge. Okay, where before, for going corner to corner in example 1, we got 3/4 R. So now example 3, it's the longest corner to corner equivalent resistance. So we're going from node A to node G. So we move the ground to node G. So likewise, the question is, for example 3, if all resistors equal R, determine an equivalent resistance from point A to point G. That's point A to point G. That's the equivalent resistance from A to G. So I went through the analysis that we're going to go through shortly, and I found that it was 5/6 R. So if you measure from this corner to this corner, it's going to be 5/6 R. And you could also do it from this corner to that corner. Say node F to D, you're going to get the same answer because of the symmetry of this object. So anyway, so in example 1, where we went from this point to this point diagonally across, we got 3/4 R. When we did an edge, when we went from, like, say, A to B, we got 7/12 R. And if we go from the longest corner to the longest corner diagonally, say from point A to G, we get 5, 6R. So anyway, as a sanity check, I went and I made one of these cubes out of resistors, because I always like to test something to verify my analytical measurements. So I built this little device here. I just took 12 small 100K resistors and soldered them all together in a cube. So using 12 100K resistors, an experimental cube was built to be measured. So I measured from point A to H with my ohm meter, and I measured 74.6K. Now the expected value is 3R over 4, which would be 75K. So that's pretty close. I was off by 0.4K here. So then I did a resistance measurement from A to B. This is my example 2. So A to B was measured to be 57.9K, but the expected value is 7R over 12, which is 58.3K. So that's pretty close. You know, there's the tolerances. I believe these are 1% resistors. That would be interesting to do a tolerance analysis to see what the worst case tolerances would give you when you measure it. And that's something that I've done a lot. Actually, you know, using the same method here that I'm going to show you, that comes in handy if you ever have to do a tolerance analysis, which I always have to do for a lot of my designs. So anyway, so if we go from point A to B, I measured 57.9 on this device I built, and the expected value is 58.3K, which is very close. I'm only off again by 0.4K. Okay, so the last point in my example 3 was going from point A to G. So from point A to G, I measured 83K. So the expected value would be 5R over 6, which is 83.3K. So that's pretty close. I was within 0.3K or 100Ks. That's pretty small, still under 1%, which these are 1% resistors. So anyway, I'm going to discuss this method a little bit and why it has some advantages over other methods that you have seen. So there have been many online videos that show you how to solve this problem. However, they are very limited and use too many assumptions to simplify the circuit. Today I'm going to show you a new technique to solve this type of problem. This technique will provide the following benefits over many of the other methods shown. As an electrical engineer, I've been using this technique for many years and have solved many hard electronics issues using this method that I'm going to teach you. So far, I haven't found any engineering textbooks that will show you this method. With this technique, you can solve most circuits. Learning this method will make you a much better, capable electrical engineer. Okay. So here are some advantages of this method and procedure. Okay, so one advantage is that you don't have to redraw the circuit to 2 dimensions, as I saw in a lot of the other videos. You could keep this in 3 dimensions, or go to 2 dimensions. This way you kind of save having to redraw this in your imagination. Sometimes doing this you could really screw up and get it wrong. 2, you don't have to do any creative thinking or make any assumptions when using this method. So it's straight through method that there isn't any ifs, not too many ifs in deciding what to do. So if you follow this procedure, you'll get the answer as long as you don't make any mistakes. So you want to minimize your chances of making mistakes. So this kind of helps you avoid mistakes doing it this way. Okay, so 3, you don't have to worry about symmetry to simplify the circuit. So in a lot of methods, it's good to know those tricks of symmetry, but we logically think in symmetry sometimes it's not a straight method. You have to be really sharp. You have to be very sharp to do it that way. So I'm trying to make this so any normal average person that isn't a super genius can solve this without looking at things that have to do with symmetry and making assumptions and things like that. Symmetry to me sometimes I consider cheating, but it gets you there, it gets you the right answer, but it's because of something you might know or realize that other people might not know. Okay, SPICE is not used or needed for this. SPICE is always good to analyze your circuits with, but this is more of a hand calculation method. That for reasons, sometimes SPICE will give you voltages and currents, but sometimes it doesn't tell you why. Like you don't see the way the circuit works sometimes. So this way you'll be able to mathematically understand what's going on a little bit better. Case 5, you won't have a high workload in having to solve the equations by hand. So all the equations are automatically solved here by a program called Maxima. So you don't, if you had to do this by hand, it would make it impossible. But by using this method with Maxima, which is a public domain program, it takes away the workload in having to solve a lot of mathematical equations. Okay, so 6, it will find a solution whether all 12 resistors are the same or different. So you could have every resistor different, the same. You could have a few of them the same, a few of them different. It doesn't matter with this method. Of course, the results come out nicer when they're all the same, but they can be different. And if you'd like, if somebody would give me one they would want to solve where all of them are different, send that to me and I'll show you how to solve that. Okay, 7, it will find a solution for all other geometric shapes, such as a tetrahedron, octahedron, etc. Whatever shape you want, it can do it. A cube is it's the geometry specific to cube in this procedure, but you can use this procedure for any other shapes. If you'd like me to do any other shapes that you would like to see, the tetrahedron, whatever shape you come up with, let me know. It has to be something that's realizable that you could actually make in 3 dimensions. If it's something like a 4-dimensional shape, I'm not too sure about that, but at least 3-dimensional shapes that are possible to do. I could try to solve it for you, or you could use this method to solve. Now, number 8. Okay, so this method not only will work for resistors, but it'll also work for dynamic passive components such as capacitors or inductors. So it will work if dynamic passive components such as capacitors or inductors are introduced, thereby rather than equivalent resistance or equivalent impedance, where transfer functions are determined rather than the equivalent resistance. So likewise, it doesn't matter. They could be all the same capacitor values. It could be different. You could have a mixture of capacitors, resistors, inductors, of all different values of the 12 different components that you could use to make the cube. So this method will work. Doesn't matter if it's a resistor, capacitor, inductor. You might be able to do it with some active components. Also, that's where if it's a nonlinearity, it gets trickier. Okay, so this method can also be used to determine all the voltages and currents in the circuit. Of course, you have to have the device being driven by some kind of voltage or current just floating in the air, and get an equivalent resistance. It's hard to figure out what the voltage and currents are. I guess the voltmeter, the way it works is, or the ohm meter, the way it works, it applies a voltage and current and drives it through the circuit to make that measurement. So it's not like there isn't any voltage or currents going through that circuit when you run the tests. So here's the general procedure that we'll go through in this presentation. So the first step is to write the nodal equations. Okay, so in our cube, there's 8 nodes and 8 nodal equations. So there's 8 equations and 8 unknowns. So that's something that is possible to solve. The next thing is use a public domain application, Maxima, to solve the equations. Note, they could be solved by hand, but that will cause a very high workload and be labor intensive and error prone. So I don't recommend, unless it's a very simple one, maybe a square or something like that. I don't suggest doing it by hand, but I'll show you how to use Maxima to solve these equations. It's very easy and makes life worth living. So step 3 is determine the drive input current. That's where I showed in the previous diagram. You want to know what the total current is coming out of your voltmeter. So depending on the node, this node had each node has 3 lines on it, 3 connections. So there's 3 currents. So you have to sum those 3 currents. So you need to know that current so I can figure out the equivalent resistance. So 4, assume the input voltage of the voltmeter was 1 volt DC. It's kind of arbitrary. You can pick whatever you want. It could be 10 volts, 100 volts, 1,000 volts. But 1 is a nice number to work with. So determine the equivalent resistance from step 3 and 4. So the equivalent resistance is the voltage in, that's this 1 volt, and then 1 volt over the input current. So I believe this is considered like Thevenin's theorem, where you could take a complicated network like this and simplify it down to an equivalent resistance. So how to write nodal equations? Okay, so what you have to do is for each node, I have one here that has 4 lines going into it. So this point is considered a node. So you want to look at it as all the currents going into the node. They're all pointing into the node. So the sum, that's really an impossibility because the sum of all currents going into the node by Kirchhoff's laws is 0. So some of these are going to be negative and some are going to be positive. But if you sum all these, some of these will have, in this case, some of them might have negative signs and some might have positive signs. But if you sum all 4 of these currents, it's going to be equal to 0. But you want to assume the direction is always pointing into the node. Okay, so that's key on writing these nodal equations. That's the convention we're going to use. So now it's time to get into the meat of this. So here's the way to solve the resistance cube puzzle. I call it a puzzle because I don't believe anybody would build anything like this. But you never know. You might have some kind of network where there's an issue and you would have to analyze something like this. I know I had in my lifetime, I've had some pretty complicated circuits and problems to solve. Using this method, I was able to save my my company, millions and millions of dollars by using this method. So anyway, so the first part is write the nodal equations. Write the nodal equations. Okay. So there are 12 resistors in the cube problem. There are 8 nodes in the cube. There are 8 equations and 8 unknowns. So here's an example of writing the equation for point A, for node A. We'll call this node A. So like I said, we assume that all the currents are going into the node. So this current here is coming from voltage B, and this current here is coming voltage from node E, and this current here is coming from node D. So these equations have a form to them that makes it easy to write. So you always see, this is the equation here, the nodal equation. So you'll always see, there's 3 of them here because there's 3 currents. So each one of these represents the current. So because of the way the direction is, the currents are always running into the node. The first term is always going to be VA. So in all these equations, you want to verify, VA, 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 and then you subtract. So this one is VA minus VE over RAE. So it's this resistance. It's always over the resistance in this path. So this is A minus D, A minus D, and that you assume this is more positive than that. So the current is flowing. Well, it depends how you look at current. So you just say that the current is positive. So you're saying what we're saying is A is in the real world. If you say the current goes from negative to positive, you could say that this is positive and this is negative, and that's the way the current flows. It's very arbitrary. So, but as long as you are consistent in the way you look at this, you'll get the right answer. So lastly, it's A minus B. So this is A, B. So we assume the current is flowing from B to A. So if the current's positive, it is that direction. But if it comes out negative, then it's actually going the opposite direction. whatever positive negative current means for you. If it's electron flow, then this would be a lower voltage going to the, this would be more negative going to a positive. And if you think it's say positive charge flow, then it's the opposite. But don't worry about that. So note for the cube, there's a pattern where there will be 3 terms in the equation. So these are the 3 terms. So for other geometric shapes, you could have 3 terms, you could have 4 terms. It depends how everything's connected. But for a cube, every node has 3 terms. Okay. So I just wanted to note that RAD is the same as RDA. The resistance doesn't change whether you're going this way or that way. So I wanted to note that each term begins with VA, and it has this form here. So knowing it has this form, it makes it much easier to check the equations for mistakes, because you always know that the first term will be this node that you're writing the equation for, and all the other terms, all the other volt nodes will be negative. These will always be negative, and you add them. Okay, so if we move on, so here are the 8 equations and 8 unknowns. Okay, so for equation 1, we did that one. Now, likewise, equation 2, you have to kind of look at the cube here. And I'm not going to go through all these examples, but so for B, it's going to be VB minus VA over RAB, VB minus VC over RBC, and VB minus VF over RBF. So this is equation 2 for node B. So this is node A. I'll put node A. And this is equation 2 for node B. And this is equation 3 for node C. Equation 4 for node D. Equation 5 for node E. So notice E begins with every voltage, and there's 3 terms and they always equal to 0. So we have node F, we have node G, and we have node H. So these are our 8 equations, and we have 8 unknowns. There's 8 voltage that are unknown, so it's always good if you have the same number of equations and same unknowns, you can usually solve it. So now we're going to put the equations in Maxima to solve them. And so I have these 8 equations, and I put them in text. I found it easier to use Notepad and put them in text, and then put them into Maxima. So that's what I'm going to do now, and we'll let Maxima solve it. So I'm going to grab this out of Notepad. I put these equations in Notepad, so I'm going to grab these. So I have equation 1 through 8, and I have a thing here to try to solve the equations. So I'm going to put that into Maxima. So here's Maxima. I just opened it, and I cut and pasted into Maxima, and then I hit cell, evaluate cells. So what I get here, I have an issue here where I can't solve the equations. I have 8 equations and 8 unknowns. And what it is, it probably has to do with the symmetry of this device, is that there's an issue here. I can't solve it because some of the equations are the same. So they're linearly dependent equations. When you have linearly dependent equations, I guess the determinant is 0 or the eigenvalue is 0. And you can't get it. There's like an infinite number of solutions, and you can't solve it. But anyway, no giving up here. We'll move on, and I'll show you how to solve it. This just gives you an indication of the problem you run into sometimes when you use nodal equations. So I made some notes here. Note that Maxima can't solve the equations because they were linear dependent due to symmetry. So some of the equations need to be eliminated. So we have too many equations that are the same. And there's an easy way to do this, especially because we're using an ohm meter. So let's try example 1, but let's do the case where all the resistances are different. There's 12 different resistors. That's a pretty complicated case. Anyway, our ohm meter is placed between point A, node VA, and node H. So let's give that a shot with Maxima. So note that in example 1, the ohm meter is placed between points A and H. So VA is known, and assume it is 1 volt DC, and VH is known, and assume it is 0 volts DC. So VH is like our ground. So since VA and VH are known, the technique is to remove Nodal Equation 1 for VA and Nodal Equation 8 for VH. So in Maxima, we still have the 8 equations, but in the solve, we took out equation 1 and we took out equation 8, and we set VA to 1 and VH to 0, saying that this is our voltmeter. So we'll go try to solve that, and it takes Maxima quite some time. So Maxima goes, and it does try to solve it, but you get a humongous equation because of all these different resistances. It is possible to compute this and maybe possibly simplify it. It probably would have been best in this area here to set some of these resistors, if we knew what they were, to their different values. If you have any ones that you want me to try, I could try that. If you have any different values for R besides them all being the same, maybe we would set R, one of them to 1 ohm, the next one to 2 ohms, the next one to 3 ohms, all the way up to 12 ohms. Maybe that would be a possibility. But anyway, you get pages and pages of equations with all these resistances, and many more pages. I'm not going to go through this, so. However, it leads to when you do this, it leads to very large equations when the R's are different. So when the R's are different, it leads to huge equations. But with Maxima, I believe you could solve these. It might be best to start plugging them in. If you had maybe one of them you wanted to vary, maybe that might be a better case to look at, like have them all the same in one vary. That might be one to look at. So anyway, to simplify this, we'll set all the R's to be the same to simplify it, as in the classical problem, all these R's are the same. But it is possible with this method to solve it with different R's. You get some huge equations, and possibly add capacitors or inductors and look at the impedances of those. So anyway, I just wanted to demonstrate that a little bit, that it is possible with this method that you can solve this problem in a pretty easy way without having to do too much math, and let Maxima take care of all the math for you, even if the R's are different. So if you have one particular one you'd want me to look at, let me know, and I'll look at that. So let's try example 1 now with all the R's the same. Now, we know the answer is 3R over 4, but we're going to have Maxima solve it for us, okay, rather than us having to do the work. So anyway, we go in, and so it's the same thing again. Note that on example 1, the ohm meter is placed between points A and H, and VA is known to be 1 volt, and VH is known, that's our ground, which is 0 volts. So since VA and VH are known, the technique is to remove Nodal Equation 1 for VA and Nodal Equation 8 for VH. So anyway, I went in, and you could still put equation 1 and 8 in here, but it's not going to do anything with it. But anyway, so the way to solve it is, you want to solve for equation 2, 3, 4, 5, 6, 7, but not 8 and not 1 for V, B, C, D, E, F, and G. And we know VA is 1 and VH is 0. So then I have some things in here that pull out those currents. And this is a way to get those currents out. And I'm going to run Maxima and show you this example. I'm going to go run it now and show that to you. So I'm going to get those equations. I saved them in Notepad over here. And this is it here. So I'm going to grab these. I'm going to grab this text out of here and copy that. And then I'm going to go into Maxima. And I'm just going to paste that. So now I go to cell, evaluate cells. So it goes in, and this is my input here, and I want to go through this a little bit with you. So this is equation 1, which isn't used. Equation 2, equation 3, equation 4, equation 5, equation 6, equation 7, and equation 8 is thrown out. So now it gives me some answers. In equation 9, it solves for B, C, D, E, F, and G. So it gives me some answers. So the voltage at B with 1 volt is 2/3, VC is 1/2 volt, VD is 1/2, VE is 1/2, F is 1/2, VG is 1/3. And so the next step is just to get these terms out. So I wanted to separate. This is a way of pulling these terms out. So I wanted to get an equation for VB, for VD, and VE. So I need VB, VD, and VE because I need to get these 3 currents, because I want to get the total current that my voltmeter is putting out. So I get VB, VD, VE, because that's what drives the current. So I get the current. So the current from A to E is 1/2R, and the current from AD is 1/2R, and the current from AB is 1/3/R. So you add all these up, you add these 3 currents up, so it's 4/3R. So since I only have 1 volt of voltage there at VA, the equivalent resistance is 3R/4, and that's the answer. So the correct answer, the equivalent resistance is 3R/4 is shown. So the correct answer is shown. So this is a very easy way to solve it. Is all I had to do is write these equations and plug them into Maxima and add up the 3 currents, and then I could get my equivalent resistance over here. So this is a very easy way of doing it in Maxima. So going back to Maxima, you can see this in here also when I solved the equations. So this is all my inputs, and this part over here is a way just to get those 3 currents to get my equivalent resistance. So it goes through all the steps, and this is my answer here. So now we're going to try example 2, which we determined. Example 2 is the equivalent resistance between point A and B, and we determined it was 7R/2 would be if all these resistors were equal to R, all 12 resistors. So note that in example 2, the ohm meter is placed between points A and B. So VA is known, and assume it is 1 volt, and VB is known, and assume it is 0 volts. Since VA and VB are known, the technique is to remove the nodal equation 1 for VA and nodal equation 2 for VB. So we have all these equations in here, but when we solve it, we remove equation 1 and equation 2. So we only have 3, 4, 5, 6, 7, 8. And then we solve for VC, VD, VE, VF, VG, VH, and we set VA to 1 and VB to 0. And these steps over here are used to figure out the 3 currents. We need to get these 3 currents because we want to get the total current that's coming out of the ohm meter, so we can get the equivalent resistance. So we'll go run Maxima, and I'll show you how that works. So what I do is I grab the equations out of Notepad that I previously put in for that case. So I'm going to copy that, and I'm going to go in Maxima and paste it. So all I have to hit is evaluate cell, and yep, when you look at it, I get 7R/12. So this is my input in green, and this is what Maxima gives me. It rewrites the equations, and I'm solving for all these voltages here. So it gives me an answer. So the rest of it here that's in here is just to extract the equations and get the 3 currents and add them up, and just take the inverse because it's 1 volt. So it's the final thing to get the equivalent resistance is to take 1 and divide it by the current, because I only have 1 volt. So that gives me the the inverse of the current coming out of the ohm meter is the equivalent resistance in this case, because it's only applying, assumed it's only applying 1 volt. So anyway, that's how I got the answer. It's very quick to solve this problem like that. So it only takes a few seconds. So here's my documentation for example 2 and how it breaks up the equation. And the correct answer for an edge is 7R over 12 is shown. So this is much, to me it's a lot easier than doing, worrying about symmetry and redrawing the circuit. This way it's a more general solution, so I can solve like anything, any shape this way, any type of circuit pretty much that's passive. This is a good way of doing it. So the last example is example 3. So in this case all the resistors are the same, but we're going to solve it between the corners, the long corner to corner. So we're going to put our ohm meter between point A and point G here. So everything else is symmetric. I think there's only 3 different situations you could have with a cube. So anyway, the answer is known between A and G. The equivalent resistance is 5R over 6 if all R's are equal to R. I put here 1 ohm, but say that was just something I was doing to make it easier, but it's really just equal to R. So anyway, in this example, the ohm meter is placed between A and G, and VA is known and assume it is 1 volt. VG is known and assume it is 0 volts. So since VA and G are known, the technique is to remove nodal equation 1 for VA and nodal equation 7 for VG. So we're removing these equations because we had linear dependence, which was an issue with solving equations. So by getting rid of 2 of the equations, because there are 2 knowns in nature, if I just had this, I guess trying to explain it, if I just had that cube floating in the air there and nothing connected to it, you can't solve it because there's nothing measuring. You have to put some voltage through it. So that's what it's kind of telling me. So I have to know at least 2 points on that cube, 2 voltages, to be able to solve the equation, to make the equations linearly independent so I could get a solution. So anyway, so this is our Maxima input. It's the same set of 8 equations again, but I remove equation 1 and equation 7 because these nodes are already known. So I have 2, 3, 4, 5, 6, and 8. So I solve for VB, VC, VD, VE, VF, VH. VA is known and VG is already known. So this is just some math here that I needed to do to get those 3 currents, because I need to get the total current that the ohm meter is providing. I'm going to show you this example using Maxima. I saved it in a text file. So I believe yeah, this was it over here, going to A to G, node A to G. So I grabbed the text here, copy it, and I'm just going to paste it into Maxima, and then I'm going to solve it like this. Evaluate cell. Ta-da! I get 5R over 6. So it's the same thing again. This is what you get out of Maxima. This is my input in green, and this is what Maxima gives you. It rewrites the equations, and it solves for the voltages. So I need VB, VD, VE to sum them up, and I get there's 3 currents again, and then when I sum them, it's 6 over 5R. And since I only have 1 volt, assuming it's 1 volt, and my answer becomes 5R over 6. So that's the solution when I'm going from far corner to far corner. So in the rest of the documentation, I put the results here, maximum results for example 3 for all R's equal R. So I could just have easily had different R's. I could have put capacitors or inductors, or use this method for different shapes. So anyway, the correct answer is 5R over 6 as shown, and that's what we got from Maxima. So this is one way to solve it, and I think it's a more general way to solve it. So this is Frank again, working out of my home lab. I hope you enjoyed this video and learned something, and this might be a good technique to solve problems like the resistance Q puzzle or many other types of electrical engineering circuit problems. So it's not just this little puzzle here is a good exercise, but you could apply it to the real world sometimes and figure out your problems, figure out what the issues might be in a typical circuit. So I hope you like this and keep on learning. Bye now.